Let's keep talking about reversible addition to ketones and aldehydes. So weak nucleophiles that can add and then come back out, right? We've covered cyanide as a reversible nucleophile. Let's go to an even weaker nucleophile. So water. Water can form hydrates. What does that look like? Well, let me back up. Those of you, especially those of you that have done research in biology, have some experience with aqueous formaldehyde solutions, formalin, right? You keep the three-headed pig alive or preserved or whatever you guys do with formaldehyde. If you were to take that formalin and take a carbon-13 NMR or even a proton NMR, you might be surprised by what you see. What you would see is absolutely no hint of a carbonyl compound. What you would see is that water has added to the CO double bond, and we get a hydrate. And this is reformed under reversible conditions. But in this case, the equilibrium constant K is about 2,000. So it's about 2,000 to 1 preference for the hydrate. Let's look at the mechanisms for hydrate formation. First, under acid catalysis. This works either under acid or under base. So remember back to ester chemistry, we said that under acid catalysis, the electrophile gets made more electrophilic. Right? Acid catalysis makes the electrophile more electrophilic. In this case, our electrophile is formaldehyde. So formaldehyde is going to take the proton from the acid. I go from this relatively weak electrophile to this really powerful electrophile. This weak nucleophile then can attack it. I end up with this tetrahedral intermediate. This is just the conjugate acid of a hydrate, and so water can come in and take its proton back, right? Catalytic acid, and I end up at the hydrate. So that's how acid catalysis works. Again, acid catalysis makes the electrophile, formaldehyde, more electrophilic. Under basic catalysis, the nucleophile gets made more nucleophilic. So here my nucleophile is OH. My base here is deprotonating water to give me some hydroxide, OH-. OH- is a really good nucleophile. So it'll react with my weakly electrophilic formaldehyde here, attack on the carbonyl like we've seen a few times now. We get this tetrahedral intermediate, which then is just protonated by water to regenerate the OH- catalyst. Right? So this is how base catalysis works. In acid catalysis, I made the electrophile really electrophilic. In basic catalysis, in acidic catalysis, the electrophile is more electrophilic. In basic catalysis, here my nucleophile is really nucleophilic, and my weak electrophile is good enough. Here are two more carbonyl compounds, acetaldehyde and acetone. So try to draw the hydrates of both of these carbonyl compounds. So here are the hydrates of this aldehyde and this ketone. Right? So the bottom is more crowded than the top, right? These methyl groups take up more space than a hydrogen atom, but this is still the smallest possible ketone, right? Any smaller than this and it's not a ketone anymore. And this is the second smallest aldehyde after formaldehyde, right? So these are still very small compounds, and yet you can see that there's a huge steric effect going from top to bottom here. So on the top, formaldehyde would prefer to be the hydrate by 2000. Acetone is hardly the hydrate at all, right? 0.2% of acetone is seen as the hydrate. That's too small to see by NMR, I think. And so this is good to remember that even though we might think about aldehydes as being important, or as hydrate formation might be important for aldehydes, hydrate formation really usually isn't very important for ketones. And the more crowded ketone I get, so if I have an isopropyl group here or tert-butyl, we'll have really zero hydrate to speak of because it'll be too crowded.